All right, good morning, everyone. All right, quick announcement, really quick. So we've had this kind of spat of students who are not actually submitting their homework on Wednesday by 3 o'clock or submitting a few minutes late. And then it starts this whole chain of emails of like them asking for forgiveness and then me relating to the TA and then finally getting credited. Just please make sure you click submit when you upload your files. And please do it on time. It'll just make life easier on all of us. We have been crediting it if it's just a few minutes late, or if the students have showed evidence that they actually created a file on time. There's usually sometimes like hours before it was due that they just forgot to submit it. Please just make sure you're doing that last bit of bookkeeping to get it in on time. Okay. All right. So we're following up on what we did on Wednesday. So just a reminder of what we did on Wednesday. We started with a really simple system. And this is just a mass spring damper system here. And we're just trying to understand some basic ideas of the workings of feedback, why it's important and what this allows us to do. And so we were starting this mass spring damper system. We said that we have the ability to apply a force to this mass spring damper system. The idea that we'd want to control the position given by C of this mass spring damper system. So just to tie this into something you may care about as an engineer, this looks a lot like a robot, actually. So robotic systems, you have some sort of mass, and you're trying to control, oftentimes, the position of this robotic arm to go to a certain location to do some sort of task. Okay, so this has relevance, even though this is a very simple system. And then we're looking at the simplest controller we can possibly imagine, which is called a proportional controller. So proportional controller just means that this block G1 of S in our feedback loop is equal to Kp, or just a gain. So subscript P means proportional gain on our system. So that means in our standard equation for feedback, we're saying that the input, U of T, should be some sort of scaling of our error signal. And just a reminder from what we learned on Wednesday, the error signal is the difference between the reference, which is our desired output. If this is a robotic system, this is desired position, and the actual measured position of a robotic system, right? So the error is a metric of how well we're doing, okay? Is the robot arm where we want it to be, or is it a little bit off, right? Is the idea. And so we started to look at this and started to understand from a Laplace transform point of view, how does this system behave when we put this mass spring damper, represented by what we call the plant here, in a feedback loop with a controller, which is the really simple controller Kp, and in a feedback loop where we're subtracting the actual position from the desired position to create our error, and we're creating this loop. So we went through, by using the Laplace transform, we wrote this transfer function that relates the actual position to the desired position, right? So if we look at this loop, the input is on the left-hand side, that's the reference. The output is on the right-hand side. And I just realized that maybe we should clarify this. So we have a term in our feedback loop called the input, or the input to the plant. But every single system has a defined input and output, right? So the input to the plant is I, or more generically call it as U. But also if we look at this transfer function, and we want to write the transfer function from C to R, transfer functions are output over input. So we're looking at this transfer function C over R. Okay, so whereas G2 may have some sort of properties by putting all these systems in a certain configuration, and Instructor Lake went through a few different examples of feedback control systems with you in class, showed you some spec sheets, right, or during recitation showed you some spec sheets of what these components may look like, but by putting them in basically buying all the appropriate equipment and putting them in this loop, we can start to construct feedback loops that look like this, C over R, and then we can write a transfer function that describes their behavior. Okay. So right before we finished on Wednesday, we got to this expression. All right, we said that C over R is equal to this transfer function, and I hope everyone's beginning to appreciate that this looks like a second order underdamped system, so therefore we can write this in its canonical form, or basic simple form. Right? So this we would say is equal to k bar, natural frequency squared over s squared plus 2 zeta omega ns plus omega n squared. Okay. Any questions about that idea, how this acts like a second order underdamped system? Okay. All right, so then the question becomes, what is the natural frequency? What is the damping coefficient? So this looks a lot like one of the problems we saw that was due on Wednesday with a fluidic system, but this is now a feedback system. So this then becomes a matching exercise, right? So we say, all right, the s to the 0 term is here. So it's k plus kp kf all over m is equal to the natural frequency squared. So then we know that the natural frequency k plus kp kf all over m, and take the square root of it. Yes?
I had a question about not the form of that, but how do you, is there a way that you just know that this is underdamped without actually knowing the full?
Okay. That's a good question. So the simple, I glossed over that quickly. So the simple answer is, with feedback control systems, you are almost always going to get underdamped systems. Well, so you can have an overdamped system that's in the left half plane. Okay, it just so happens we're injecting energy into the system by having a feedback loop. Okay, because we have some sort of controller that's oftentimes amplifying the air signal to create the input, and so in a certain sense we're injecting energy into the system. So even systems that are naturally very well damped themselves, like the plant has a lot of damping in it, will result in underdamped systems. Okay. And we'll talk about this a lot. We'll show how pretty much every system is going to look like a second order underdamped system. It's for a system to be in a feedback loop and still be overdamped, you have to be like trying to move concrete or like concrete. Something has to have a lot of damping for that to happen. Thermal systems are where you see it the most. Thermal systems like the room, the time constant of this room is very, very, very slow, right? So if I were to light a fire in that corner of this room, someone on the other side of the room wouldn't feel it for a long period of time, right? So thermal systems are often overdamped, but anything that's fluidic systems, mechanical systems, electrical systems, you're almost always going to be underdamped. So this is kind of a generic case that wouldn't apply to everything, but it applies to most of the cases we'll see. All right, thanks for that question. So we have our natural frequency is given by this. I want to point out a discussion point from Wednesday just to reiterate this. So on Wednesday we said, okay, one of the, I guess, beauties of feedback control is that we can change the behavior of a system quite easily, right? So there's basically two ways which we can think of how to change the behavior of the system. We could buy all new components for a robotic system, which requires basically disassembly, buying new things which cost money, and reassembling, which costs money. Or, so that would be changing like our parameters K, M, KF, right? That would cost a lot of money to do, or because we're using controllers built into this, we can simply just change this parameter KP in a line of code on the order of about a minute, and that changes the behavior. So if we increase KP, we see that our natural frequency of our system increases. Right. So K, KF, KM, all fairly difficult to change. KP can be changed with a keystroke, really easy. So we have this expression for natural frequency. We can also have an expression for k bar. So if we know that the term in the numerator here is k bar times natural frequency squared, that equals kp kf over m. Okay, so inserting what the natural frequency squared equals, that means k bar k plus kp kf over m, kp kf over m. These m's cancel. That means that k bar equals kp kf. K plus kp kf. Okay, so again, the gain on our system changes with this value kp. So if we were to, say, change kp from a 5 to a 10, that would change this k bar, right? So now you see this is in both the numerator and the denominator, so we'll talk about what that means in terms of performance in a second. Last term, we have the s to the 1 term here. Sorry, s to the 1 term is b over m, and that matches 2 zeta omega n, right? So we have then 2 zeta omega n is equal to b over m. So then I have that 2 zeta omega n is square root k plus kp kf over m. And then you can simplify this to be zeta is equal to b over m. To natural frequency and then simplifying even further, okay, gives us this expression. Okay, so again, kp, this term that's very easy to change, shows up in terms of our expression for zeta. And so we can see if kp gets larger, zeta gets smaller, right? So the system becomes even more underdamped, or the damping coefficient goes down, right? With this expression. Yes?
Is that MCK?
No, that's a parentheses.
Oh, okay.
Make that a little more clear. Thanks. Any questions about this idea? About how changing something in a computer can change the behavior of the entire system? Or microcontroller, whatever you have connected to it. Yes?
What does KP like physically mean?
Okay, so that yes, let's take let's like use an example of Instructor Lake showed this example of this robotic gantry system in the recitation on Wednesday, right? So a robotic gantry system, the objective there would be to position one of the axes, right? So X, Y, Z. Let's just pick, like, say, the X-axis, right? So we would have some sort of reference, which would be where do we want the X-axis at all points in time to do whatever the robotic task is. Maybe it's going to some location, picking up something, and going back, right? So the reference trajectory would say it's to go somewhere and then come back. The reference trajectory would look like, all right, so go to this location. We want it to go location A, and then come back, right? It would look like something of this signal, right? So then the error would be what our actual response looks like, which is not going to be perfectly equal to the reference. And we'll talk about why it's not perfectly equal to this a lot in this class, but let's just assume it's not going to be perfectly equal to this. But say it looks like, this response. So that means that our error signal, so we can label this would be C. This would be R. Our error signal, all right, so error is reference minus actual, right? So the error signal is going to be positive value for about this amount of time. That is not as blue as I want it to be. Let's see. All right, let's try that. So the air signal is going to be positive up until here. So it's going to go like this, be about the same. That's going to dip below. Which creates a current. If you go back to your discussions of motors, torque or force is proportional to current, right? And if you look at a standard motor. And so what this is saying is, okay, so our air is positive here, right? So this means that we're going to have to give some sort of positive force because we're lagging the reference. So that's pushing the robotic system in the positive direction. And then when I reverse position, then the force is going to have to be negative, right? So this is all coming from the sign of the air. And if I have, say for instance, this is our air signal, my input is a proportional gain of that, right? So if we're using proportional control, it's going to be the air signal times Kp, and that's going to be what we're actually sending into the system. So say, for instance, Kp is equal to 2. That means my input signal is going to be, this is my best approximation of twice that signal. It's going to be equal to this, right? And if my Kp was 10, then it'll be 10 times that much. So I'm putting more effort per unit of air if Kp increases. And so you can think of this gain as being how aggressive your control system is. And we'll spend a lot of time talking about kind of relative aggressiveness of controllers and what the positives and negatives of that are. Yes? That's a difficult question. There's a lot that goes into that in terms of like changing a physical component. So I can't answer that in like the general case. It's very specific to what the situation is. It's more of a design decision. So when there's certain systems that are inherently difficult to control and some are easy to control. We'll talk a little bit, but not too much. Systems with right half plane zeros are difficult to control, but that's a big question. I don't have an answer that I can explain now. Okay. All right, so what we've seen is that this value Kp can change some of the fundamental characteristics we care about in a response. And we're going to spend some time now talking about the step response, or basically the response of a second order underdamped system to some sort of, it's basically the response of a second order underdamped system. And so second order underdamped systems, I hope you can appreciate from everything you've learned in, say, 3260 in this class so far, has a general form. And this is nice because we can start to describe behaviors of a system for this general form in very generic ways. Okay, and so if we look at the denominator of this transfer function C over R, this specifies where the poles are. And if we look at the poles of a second order underdamped system, they are precisely at this location. So this is just setting this equation equal to 0 and solving for S. And those are our poles. These are P1, P2. So this would be the poles of our system. And if we look at and simplify this, we see that the poles are at negative zeta omega n plus or minus omega n square root of zeta squared, or square root of zeta squared minus 1. And so we're going to talk about these relationships a lot for the next few weeks, actually. This is going to be something we're discussing all the time. The main point here is that we can describe the real part of this pole, the imaginary part of this pole, and some other factors here. So if we wanted to know what is the distance of this pole location to the origin, that would be then using Pythagorean's theorem, right? This would be square roots of zeta squared omega n squared plus omega n squared 1 minus zeta squared, right? If we're using Pythagorean's theorem. And if we were to simplify this, we'd see that, all right, square root squared, right? That just simplifies into 1 minus zeta squared. That means this term and this term cancel out. And we get that the rate, or basically the radius of that pole location to the origin is the natural frequency. Okay. Other metrics that we can look at is what is this theta? And this theta is, okay, so the opposite end is zeta omega n squared. The hypotenuse is omega n. And so that we see that this angle between the imaginary axis and this pole location is inverse sine of zeta. Okay. So as the natural frequency increases, this pole location travels along the set angle from the imaginary axis and just dilates out, right? So if I were to double the natural frequency of a system without changing the damping coefficient, it would move out to approximately here, right? So it would go along this angle and just expand out from the origin. If I were to change the damping constant and not change the natural frequency, the distance of that pole from the origin would stay the same. It would just rotate either closer to the imaginary axis or farther away from the imaginary axis. Okay. Does that make sense, kind of the behavior of these, of the pole locations? All right, so here's that's the basic map of the pole location. Some other terms that we probably have seen before, but we'll find valuable in this class, is the damped natural frequency. Okay, so the damped natural frequency, even though this may have been a term that you've seen before, I don't know if you've seen it in this case, like in this context before, but the damped natural frequency, which is equal to omega n square root of 1 minus zeta squared, is just the imaginary part of that pole. Nothing more complicated than that. We also have a term called the decay rate. Zeta times omega n. Decay rate is simply just the real part of this complex conjugate pole. That's a pretty basic definition. Okay, and so with this, we can start to understand what something is called the step response. So we'll be talking about the step response over and over again in this class. And so the step response is kind of our canonical input to try and understand what is the change of our system in terms of the change of, say, position or whatever the output may be to a step change in reference. Okay, so we explained just a little bit ago about the idea of a robotic positioning system where we say, okay, the reference signal is specified such we go to some location, we pick up something, and then we move back, right? So that is a more complicated form. I drew this kind of smooth line, which is how you expect a robot you'd want it to move, right? Kind of a smooth fashion. So the Laplace transform to describe a trajectory like this is fairly complicated. So where we start this problem out with at the undergraduate level is instead of looking at this more smooth version of the reference signal, let's take a look at the simple task of saying, I want my reference to change from a position, say position works in this example, a position of 0 at time less than 0 to now a new position. And we use the generic position A bar. All right, and so we're saying to whatever the system may be. So this could be temperature. We're saying, okay, temperature at a certain time, a point in time that we care about, change the temperature of this room from whatever it is right now, 70 degrees to 73 degrees. And so that would be you going over to the thermostat and pushing it up to 73 degrees. That is essentially a step change in reference. This could be cruise control in your car, right? So you're saying cruise control go from 60 miles per hour to 65 miles per hour. You have almost an instant said change the reference velocity. And then in a robotic system, this could be, say, going from wherever you're at right now, move to the position A bar at a certain point in time, right? And it's a very simple input we can start to understand behaviors with. And so the step response is going to be something really fundamental that we'll start discussing pretty much all performance with, is the step response. Any questions about the idea of what a step in reference means? Okay. All right, so if we have this step response, in the time domain, this is R of t is equal to A u of t. And that means that in the frequency domain, again, for those of you who were not here on Wednesday, we are from now on essentially going to be dropping the S term on all signals, assuming that we're working in the frequency domain. We're going to be working in the frequency domain so much that that's going to actually be the most common case. And so, forgot my notes have this as A, not as A bar. So let me remove that bar there. So R of S in this case is going to be equal to A over S, if we're saying that is what a reference signal looks like. So if we have our transfer function, all right, so as a reminder, this is C over R. If we're looking at the step response, we're saying, okay, we know what R is. Now let's calculate what C is. And then let's calculate the time domain response so we can start to quantify and understand how the system behaves for different values of Kp. So that means if we know C over R, that means we can write C. Okay. And then I'm going to skip the next steps because this looks a lot like some of the homework problems we've done thus far. So this is the case of we have a second order underdamped system with an extra pole at the origin, and then we're doing the inverse Laplace transform of this. So this happened, we saw this on homework 5, right? And then we've seen this in a few different locations as well. So this, if we were to then take the inverse Laplace transform of this by using the Laplace transform table that was important on homework 5, right? So that was given on the quiz. This would be inverse Laplace transform. We would get that C of t is equal to k bar A 1 minus e to the negative sigma d. Remember, this is our decay term. cosine omega dt plus sigma d over omega d sine omega d t. So this is what we're going to call the step response of a second order underdamped system. And then furthermore, we can actually simplify this a little bit more. So this is going way back. This is going back to lecture 2. We talked about if we have a sine wave and a cosine wave of the same frequency, we can write this as a single cosine wave with a phase shift. So this is going pretty far back now, multiple weeks. But the expression for this, if we want to get to the terms of a single cosine wave, so it's scaled by the coefficients using Pythagorean's theorem, and cosine omega d t minus phi, where phi is inverse tan sigma d over omega d. Okay, so in terms of actually writing this out or doing the inverse Laplace transform, that's something that you're not really going to have to do very much from here on out. We're more placing this here to try to understand some relationships. Okay, and so these relationships, we're going to start to, in a second here you'll see it, but we're going to plot this out. We're going to try to understand how these different terms affect what we call the step response. So, okay, so what I'm showing here is this plot. And this is this function that we just wrote down. Okay. So some features of this that we'll go through. One is that our step value is A. Okay, so think of this as a robotic system. We're saying the desired position is going from 0 to A at time is equal to 0. And given the Laplace transform we've written to describe how this feedback system works, and doing then the inverse Laplace transform, we know that then the response of the system is going to follow this behavior here. Okay, so let's talk about what happened here. So we said, okay, robotic system, we want you to, at time is equal to 0, to instantaneously move from point 0 to point A, right? In your understanding of physics, right, you know that you can't just instantaneously make a mass move from one location to the other. You can't teleport, right? So, but that's what we're asking it to do if we're putting a step function into it, right? So we're saying going from here to here instantaneously. What this is telling us is that the actual system is not going to perfectly behave like that. It's going to go a certain distance. It's going to oscillate a little bit, and then the oscillation is going to decay, and then it's going to settle at some location. And with proportional control for the type of system we're talking about, that final location is actually going to fall short of A every time. Okay, for the system we're talking about. We'll talk about other cases where it will not fall short, but for a mass spring damper system with proportional control, it's always going to fall short of that. Okay, so A is here, we react, oscillate, and then we fall short of A, right? Sorry?
It says proportional.
Proportional control, yeah. We'll talk about ways to improve upon this later. Okay. So what this is telling us is that it did something resembling what we wanted it to do, right? It moved in the right direction, did some good things. It didn't quite do everything we wanted to do. But here's where we're going to start for this discussion in terms of trying to understand the response. So any questions about like kind of the correspondence between this plot and like if you were to watch a robot going, what it would look like? Yeah. Yes, Tyler.
If you increase the proportional term, will bring your final value closer, but you'll have more oscillations.
Yeah. You're done with the class. Yeah. So, yes, exactly. We'll talk mathematically why that's true. Carson.
Since there's still an error in the steady state, it still tend to go that direction, just very slowly.
It will not. So this is the proportion of gain, right? Is the proportion of the air, but you also have a spring constant that's always trying to bring the system, a spring always trying to bring the system back to its equilibrium. So what this has found is a static equilibrium between the multiplication of the air with the proportional gain, whatever that force corresponds to, and the spring force. Yes.
So the point of adding the like the control is that we can now decrease the I'm trying to we've made our oscillations smaller than they would be. I guess without the control we couldn't have told it to go anywhere.
Yeah, so you could do something, right? If you had just, so this gets back to the whole discussion of what open loop control would be versus feedback control. So here's our standard feedback controller, right? If we had, if we didn't have a feedback control, that means that we cut this line here, right? And you could just put in, okay, you say I want to go a distance of 1 meter. And you could have a general idea, and that's actually what project part 2 is asking you to do. You could have a general idea of how much input into your system is required to move a certain distance. Part of the difficulty of that is you have to know your spring constants very, very well. And if you don't know that perfectly, you're going to be off. Okay, so if this response is, you say, Professor Helsley, this response looks like it really sucks. Why would we ever do this? Trust me when I tell you that engineers have figured out how to improve upon this. Essentially. Right. This is like the simplest thing you can do, and we'll talk about ways in which you can improve upon this response as well. This is, you can think of almost as like the simplest controller we can make, and it has some deficiencies associated with it. We'll build up to making better ones in this class. Right. Okay. So we've identified that this response is not favorable, right? If we had a robotic system, we'd want it to perform better than this. And so if we want to say, all right, let's make our response better, it helps to have some sort of metrics on this behavior. So people in the controls community have defined how we characterize this step response so that we can say, all right, this controller is better than this controller, right? Maybe that'd be a good comparison we want to make. And so these metrics we'll go through now. The first one is called the rise time. And so the rise time is given on your chart here. So rise time this is kind of a fuzzy definition. It's not the most precise one, but it's generally accepted as the time at which the response first reaches the vicinity of the new steady state value Okay, so usually, vicinity is a fuzzy word, right? But this is generally defined as, usually this is 90% of the new steady state. Which we're going to define as C final. So you can see this is already on the chart here. The new steady state is going to be C final. And we have expressions for this. The expression for rise time is more of a rule of thumb. So this rule of thumb, so when we say rule of thumb, it means that the expression is actually much more complicated than this, but this rule of thumb that we'll use in this class, and it's widely accepted, is that the rise time is equal to 1.8 over the natural frequency. Okay, so this means that if we, and we'll get into these relationships with a little bit more care in a little bit, but we can look back at our notes before that the natural frequency is a function of Kp. If we increase Kp, natural frequency goes up. So that means that rise time would go down. Right? These are natural frequencies in the down. Okay, so that means if we make our, and I think this makes sense, if we make our controller more aggressive, it'll take less time for the response to shoot up, right? Because we've said before, if we have an error of 1, let's make our proportion of that, say, the input 1 times that, that's proportional gain of 1. And now we're saying if we have an error of 1, let's make our proportional gain 5, that'd be 5 as our input. So we've made the control system more aggressive, right? If we increase our proportional gain. Other metrics is peak time. That's the time at which the response reaches its maximum value. Okay, so we can actually directly solve for the peak time. All right, so here is our response C of t. Right, and so if we want to understand what is a peak or a valley in this response, we're looking at maximization or minimization of this function, right? So going back to your calculus classes, right, this would be taking the derivative of this expression with respect to time and finding the root of that derivative, right? And that would be the peak time. So the notes give this in its entirety. You can take a look at that if you want. The main idea here is that we're setting dc dt equal to 0, solve for t, and that's going to equal our peak time. Oops. Okay, so if we look at our chart here, the time at which the response first equals, or I guess not first, the time the response hits its maximum value is this time here, right? So here's the maximum value of the plot. This takes TP seconds. Okay. All right, so if we were to do what we just said here, set dc dt equal to 0, solve for t is equal to tp, we would get that Tp is equal to pi over the damped natural frequency. And this is actually an exact expression. So contrasting that to the rise time, which we use approximately equal to for expression, approximately equal to 1.8 over the natural frequency, Tp is actually equal to pi over the damped natural frequency. Okay, C final, this is the steady state values. This is, all right, so we said robotic system, go from 0 to A. It actually settles out somewhere short of A if we have a mass spring damper system with proportional control. And so our expression for this is we just take the limit so C final equals limit, time goes to infinity of C of t equals limit, and I think it's probably easier just to look at the response here. So here's our expression for C of t. Okay, so a cosine wave oscillates between -1 and 1, right? So as we take the limit of cosine, this doesn't either converge or diverge. It just stays in this oscillatory manner between 1 and -1. But an exponential to a negative coefficient as time goes to infinity, goes to 0, right? So this entire, whoops, didn't mean to write that. So this entire term on this right-hand side here goes to 0, and then we just have k bar a as C final. So if we look at then our plot, we have C final, right, which is where our response eventually settles down to. Again, like I said, with a mass spring damper system with proportional control, it's always going to be short of our desired reference. And we can also define E final, right? If the error is the difference between the reference and actual, this would be then E final. So E final in this case would be some non-zero number. Okay. Any questions on those thus far? Metrics. Okay, settling time. It's the time after which the response will stay within a specified range of C final. Okay, so this is again kind of a loose term that is not very specific, but in general, in this class we'll be talking about 2% settling time. So in this class, 2% settling time, so this would be the time after which the response will stay within 2% of this new C final. All right, so the way in which we would draw this on the plot is we would look at the step response. We would draw some bounds about this response and say, all right, here is plus or minus 2% of C final. And then we look at the last time at which the response is outside of this bound. All right, so this is going to continue to oscillate forever because e to the negative sigma dt only exponentially goes to 0. This will oscillate forever, but it is going to pass this threshold at some point, and we label this threshold TS. Yes?
I think it's a little weird that your C final's below your final step, and isn't that because, like, the reason why I think it's weird is because it's constantly in a loop and it's constantly measuring your error.
Mm-hmm.
So it shouldn't be always trying to minimize your error, so it wouldn't always be trying to get to having error be 0, or is there like a numerical method to it there's like a difference?
Yeah, so that this is it's a balance. So I agree. The error is always going to, if you look at E final, it's a positive number, right? So the system is always going to be putting a force into the system, right? If we look at a mass spring damper, this is a mass spring damper with a force applied to it. So the force is always going to be some non-zero number, something greater than 0, pushing it in the direction of A. But we also have a spring on our system, and that's pulling it back. So what it reaches is kind of static equilibrium between the factors of your gain between your input and the force, the proportional gain, and your spring constant. Is what it's all reached here. And we'll come up with the actual expression for that. I hope that will give you an actual expression for what that static equilibrium is in a second. Yeah. Yes, Carson.
If you have the expression for that difference, and you add that to the controller, is that the same as that thing, or is that a different scheme?
That'd be different, yeah.
Sorry.
Integral or?
No, just adding, like knowing the offset.
Oh, yeah. Yeah, what you're talking about is called feed-forward control, which is outside the scope of this class, but yeah. Okay, so 2% settling time. The approximation that we're going to use in this class is that the settling time is approximately equal to 4 over sigma d. This is, again, not an exact relationship, unlike TP. It's an approximation. And then we have, I think, just one more. Yeah, we have one more. So then last one is overshoot. Percentage that the peak value, we'll label C max in a second, exceeds the steady state value. So let's do this one schematically or on the chart in a second to see what we're talking about. Okay, so the very height of this plot is, what do we call it, C max? And so we look at what is this distance? And this is C max minus C final. And then our overshoot will be equal to C max minus C final. And it's always a percentage. And so it's going to be divided then by C final. Okay? So it's basically how much our system, the word's pretty illustrative, overshoots the final value, right? Okay, so this expression is fairly complicated, and we'll write it here once and never use it again, just so you can see it. And the main point of writing this out is it is just to show that it's purely a function of the damping constant. Okay, so no calculators in exam. We would obviously not expect you to calculate what this is without the aid of a calculator. So on every exam going forward, so note, underdamped systems, right, we always had a zeta is between 0 and 1. So on every exam or test you're going to have from here on out where this is going to be required, you'll have this map. And so this is sufficient. Okay, so if you say overshoot of 50%, right, you would then carry this over and you say, all right, that is a damping constant of approximately 0.22, somewhere in that range, right? 0.21, 0.22. All right, so this chart is going to fill in for that, find that equation. Okay, so things to note, zeta ranges between 0 and 1, right? This is the case of 1 is critically damped. Overshoot goes to 0 as we get to critically damped, right? Maximum overshoot ranges all the way up to 100%, nothing more. For second order underdamped systems, this happens at a zeta is equal to 0. Okay. All right, so we're out of time. We just have 1 minute left, so I want to open up the questions. On Monday's class, we're going to talk about how this parameter Kp affects all these different metrics. Okay, so we'll get into that, which we had some questions kind of alluding to that today. So we'll hopefully answer all those. Any general questions about the step response before we adjourn for the weekend? Okay, have a nice weekend, everyone.